Very good. Hello. In the last class, we were discussing a fair amount of the last classes. We were discussing a fair amount of the mathematics that lies behind quantum mechanics. Uh, what I want to do now is continue along those lines and more or less complete this topic. So let me go to my tablet. Here it is what we were doing last time. The idea was if you impose on the space of probabilities that you have a symplectic structure and a metric structure, and you look for those congruences, those families of curves that fill the whole space, the whole phase space. Then, by imposing that these two structures be conserved, what you find is that the families of curves that preserve these structures are Hamiltonian flows. What that means is that there exists a Hamiltonian function, and that the Hamiltonian function ends up leading to linear flows, which means it is bilinear. It is linear in the complex conjugate and in the wave functions. So that when you actually take the equations of motion, which are given by Poisson brackets, you get an equation, a Schrödinger equation, that's linear. So what we would like to do now is, now that we have equations for how to obey these conditions, the preservation of these two structures, now that we have equations that happen to be linear, let's take advantage of that feature. What linearity does for us is that if you know of one solution and you know of another solution, then you can actually create other solutions by doing linear combinations. This no longer involves any assumptions here. If this is the equation for the curve, if you have one solution, you have another, you find a third one. Now, the remarkable thing here, though, is that these are solutions, these are Hamilton killing flows on the embedding cotangent space, not on the actual space of normalized probability distributions. So while it is true that you have this linearity on the larger embedding space, the linearity does not work as nicely on the space restricted to normalized probability distributions. You can still get things of this sort, but the constants have to be chosen appropriately. They're not as powerful. So the linearity is something that's there. If it is true, if you have one solution and I have another, then you can build a third one. But it's not expressed in a way that we can take full advantage of it. So we would like to clean that up a little bit. Okay, very good. Let's proceed to do that. In fact, let's actually write it. Make the following point. Note that if you have one solution and you multiply by a constant phase factor, this state is equivalent to the first one. I can do the same thing with the second one. If you have your second solution and you multiply it by a constant phase factor, this first state, psi 2, is equivalent to this. They lie along the same rate. But if I now construct the linear combination, this is not equivalent to psi3 unless, of course, nu1 equals nu2 equals nu3. So it's not equivalent to something that would be equivalent to this one. So what this is telling us is that, well, we have problems with the normalization. We also have problems with what we consider as the physically reasonable relevant states, those that lie on an array. So while it is true that the equation is linear, this equation is linear. There is no two ways about it. If you have one solution, you have another, you can construct a third. It is not true that this mathematical linearity translates into a full-fledged physical superposition principle. If this is a physical solution and that's a physical solution, it's not necessarily the case that this is the psi3 is going to be physical in the sense that it is normalized. We want to clean that up. So the note that is important, the mathematical linearity does not translate into a physical superposition principle. This is sort of interesting because it's an opportunity. This is telling us that by understanding better what this mathematical linearity implies, we might get further insights into the superposition principle in physics. But that's for later. Then that's when we're actually doing physics. Very good. So let us do that. So what we want to talk now is about the introduction of Hilbert space. It might seem a little bit surprising to you that we have talked a fair amount about the mathematics of quantum mechanics at this point, purely from the probabilistic point of view, as flows in probability spaces, but we never mentioned Hilbert spaces. So where do they come from? And so what we have to recognize here is that the equation here is linear. Given two solutions, we obtain a third. So we definitely have a linear space. These psi's form a linear vector space. Form a linear vector space. Now by vector here, we're talking vector in the sense of linear algebra. Namely, the idea here is it's a vector in the sense that if you have one object and I have another object of the same kind, and you manage to add them in such a way as to produce yet a third object of the same kind, then we're talking about vector spaces. All right? So it's linear in that sense. We do not, at this point in the game, think of these psi's as being tangent to any curved space, to any manifold. So that would be a more geometrical way to think about vectors. This is more the algebraic way of thinking about vectors. You have two objects of the same kind. If you add them, you obtain something of the same kind. You call that a vector. So the psi's definitely form a vector space. We would like to make it into a full-fledged Hilbert space. We would like to introduce a inner product, an inner product. At this point, we don't have an inner product. We have these vectors, these psi's that can be added to produce other psi's. but we do not have an inner product. Now, fortunately, and this is what makes the introduction of the inner product not just a matter of an additional ad hoc additional assumption, the ingredients to come up with an inner product are already there. What we're going to do is we're going to say, look, we already have a metric tensor and a symplectic form. We have tensors that are kind of natural in this setting. So we would like to construct an inner product without adding anything new, without any additional assumptions. That's the crucial element. We don't want to just, in an ad hoc way, say, well, we want a Hilbert space. No, the Hilbert space has to be there contained in what we have done already before. And so we're going to do that. We're going to say, look, we have this metric tensor. It comes with components, and we're going to multiply that by the various points that the coordinates that describe our states on the statistical on the cotangent bundle. So here we go. We contract with mu I, contract with mu j. So this is like a scalar product of the 2 points, but it's not a scalar product of vectors. Please notice this is important. When we apply, we sum mu I and mu I, we sum those indices. Notice that these guys here are not vectors that are tangent to curves. That's not how we define this. That's just the coordinates of a point in this so these are points in here I should in T star S plus 1. They're points, they're not vectors. In fact, here I should talk about 2 different points. So let me call this phi. 2 different points. Now we also have an omega, and we can do the same thing, and we have complex numbers. These are all complex numbers. So we can try to define an object like this. This object has a number of interesting properties. And this is what we're going to say is the inner product of these 2 vectors, psi and phi, in this linear vector space in the algebraic way. Note, these are not tangent vectors to the space. They're just points in the space. Vectors. Very good. So this is how we define an inner product. Once you see, I didn't introduce anything new. This was already available to us. That's what's really important. So what does it buy us? First and foremost, when we actually substitute what these guys use the fact that when we have these points, there is a psi 1i, there is a psi 2i, and these guys are the wave function and the imaginary unit times the complex conjugate. When I substitute these mu i's here over there, what I get is that psi phi is equal to let's get it right. It's convenient to introduce a 1/2 there. And when we do that, this is 1/2. This is psi I. I psi I complex conjugate G plus I omega, and then here phi I phi I complex conjugate. Now these matrices, we know what they are. G is I 0 1 1 0. Omega is, oh yes, and there is delta ij, and omega is 0 1 minus 1 0 delta ij. Let me just check to get this right. The metric has a minus sign. There is a minus sign there. Okay, so we plug these matrices here, we do the calculation. Lo and behold, this is what we get. So we have a standard formula for the Hilbert inner product here. Very good. So here, as you see, I have reverted here to doing the Dirac notation. There is one thing that we can see immediately from something like this, from this expression. Let me do it here. If we want to preserve the inner product, we need transformations that preserve the metric and preserve the symplectic form. Transformations that preserve the symplectic form are symplectic transformations. The space has two n dimensions, and it's basically a real space. So symplectic transformations, these preserve omega. We want also transformations that preserve the spherical symmetry of the space. So these are orthogonal transformations in two dimensions, in two n dimensions. These are the ones that preserve the spherical symmetry of the metric. If we do transformations that include both, so we have here the intersection of those transformations that are symplectic and orthogonal, what we get is something that preserves the inner product in this Hilbert space. These are transformations in unitary transformations in n dimensions over the complex numbers. So this is how you see that the Hilbert space inner product leads to unitary transformations. This preserves the inner product. Very well. What else can we do with this? Now we just we've done everything we want. What we have to do now is just read off some properties out of this. So we can check that the inner product is positive definite. If you do the inner product with itself, of a vector with itself, you get something that is obviously positive definite with equal to 0 if and only if the vector itself vanishes. Let me see. Furthermore, we can expand we can introduce a basis of states, call them like that, so that the relation between these vectors in the Hilbert space and the wave functions is something like that. With these vectors here being orthonormal, just a matter of substituting what you have. If you have one of these vectors can actually be expanded, you can do the inner products here by just putting a bunch of zeros and ones, and you get this formula here downstairs. And furthermore, these vectors form a complete basis in the sense that any state psi which can be expressed in this way can be recovered from the basis. Anyway, so that's just sort of like a standard mathematics that goes with this. So how do we visualize this vector space? Because at this point, if you look at this, what we have here is, on the one hand, we have these points with n coordinates that are complex, and we decided that these points form a vector space. But these are points in this cotangent bundle, while here we're saying, since they are elements of a vector space, we can actually introduce an inner product. So the question is, how is this vector space connected to the cotangent bundle? How is the Hilbert space related to the cotangent bundle? In fact, if you think about this, an expression of this form that embodies the linearity of the whole thing, and that led us to discuss vectors in a Hilbert space. When you have a curved manifold, does it make any sense to add 2 points? What does it mean to add 2 points on this space on TS T star S plus 1 on that cotangent bundle? Clearly, we need to understand this space better. What does it mean to add 2 points? We can understand what it might mean to add 2 functions, but not 2 points. Well, we had mentioned that we wanted to describe the phase space, the epistemic phase space, by embedding it in a larger space that is spherically symmetric. And I said spherically symmetric, but if you recall, there was a wide variety of possible spherically symmetric spaces that we could use. In fact, maybe the best way to think about, to visualize what this Hilbert space might be, is choose the embedding space as being flat being a flat space. Basically, it's the space of two n-dimensional flat space over the real numbers, Euclidean space. You can do this. If you recall what the metric of this guy is, just go check up previous lectures. You would see that there were two constants in that metric. So the choice that we adopt is put that equal to 0 and this equal to 1, and you're going to see that then the embedding space turns out to be flat. This is interesting because if the space turns out to be flat, the Hilbert space is the flat version of the embedding spaces. What is interesting there is that whenever you have a space that's flat, let me draw a flat space here, flat. If you draw a curve on this flat space, then each point on this flat space can be thought of being given by a vector. So here you have the Hilbert space. It's flat. Each point is a vector. But then the tangents to curves are differences of vectors. And they, of course, are vectors themselves. So here we have a situation where the tangent vectors, the vectors that are tangent to the cotangent bundle happen to be coincide to be of the same type as the vectors in the Hilbert space. This is in fact what makes a space flat. It's when, if you have a curved space, tangent planes, tangent spaces are not the same, cannot be identified with the curved space. But the moment that the underlying space is flat, the tangent spaces are all identical to each other and they can immediately be identified with the base space itself. So this is what we do with this magic trick here of setting the embedding space to be flat. Not only it is completely isomorphic to the Hilbert space, but it also allows us to identify tangents to curves with the points themselves, objects of the same type. Very good. Let's proceed where let's talk about Hermitian, how it is that Hermitian operators, so Hermitian and unitary operators arise. The idea here is that, remember the Hamiltonian functions? The Hamiltonian function was supposed to be bilinear in the wave function and its conjugate momentum, where this is just a matrix that happens to be Hermitian. Well, okay, those are the Hermitian operators. And so the idea here is that if we write this in terms of in the Dirac notation, this is going to be written as an expected value. The Hamiltonian function is the expected value of the corresponding operator. And evolution flows are going to be described by you can see here that I wrote the flow for psi I, and here I'm going to write I k psi. What I wrote here is the sum over j of k I j psi j. So the correspondence here is I dd lambda equals the corresponding kernel. So this is the flow written in Dirac notation, and it can also be written alternatively. We can write it as psi lambda, the vector as a function of the parameter lambda is the action of an operator on an initial state where the operator, hat k lambda is equal to the exponential of minus I k lambda. So there you see how it is that everything we had done before can be translated into this new language in a Hilbert space. To end this, I would like to talk about commutators. And I suggest you strongly go over the algebra, try to see how the algebra works out, because it's extremely natural and clean and simple and enlightening. How do commutators work in this environment? Suppose that we have two vectors. Let two Hamiltonian functions. We have two Hamiltonian functions. And of course, from these Hamiltonian functions, we can find the corresponding vectors and the corresponding Hamiltonian flows. So let us compute what the corresponding Poisson bracket is. And we just write it out. The Poisson bracket is going to be the derivative of u with respect to psi I, derivative of v with respect to the conjugate momentum minus derivative of u with respect to the conjugate momentum, derivative of v with respect to the coordinate. So that's the definition of the Poisson bracket. If we now translate this into the language of state vectors, the derivatives, which is something that comes from say, here. Here we have derivatives of the functions with respect to the psi's, and then the psi's with respect to the functions. If we do that, then this is what we get, that the Poisson bracket is equal to minus I, the sandwich of the actual commutator of the corresponding functions. Now, this is interesting because one of the things this does is it shows an explicit correspondence, an equality between the Poisson brackets that we normally use in classical mechanics and the commutators that we use in quantum mechanics. And you see that this is an equality. There is a sense in which this is much better than Dirac's original conjecture, that somehow the commutators of classical mechanics, the Poisson brackets of classical mechanics, were analogous to the commutators of quantum mechanics. That was an analogy. The commutators were referring to momentum and position, and the Poisson brackets to momentum and position. And these are completely different objects, because on the one hand you have operators, and on the other hand you have classical quantities, classical variables. What we see here is that this is no longer an analogy, it's an equality, but the Poisson brackets refer to probabilities and the corresponding canonical momenta, while here, what we have here is an expected value of the quantum commutator. Very good. So we're done. We did it. We have the whole formalism of quantum mechanics under control. So the question that remains is this all there is to quantum mechanics? And the answer, of course, is no. All questions concerning physics remain open. Okay, interpretation. So the physical interpretation remains open. And of course, for physics, that's all that matters, right? It's no use having a mathematical framework unless you know how to make connections with experiment. So, for example, when you have a probability that we wrote as theta I, what is I? That question has not been touched. Is presumably I is ontic. Are there other ontic variables? What is real here? How about observables? Presumably these objects here that we called with a hat, these kernels, correspond, that happen to be Hermitian, correspond to observables. But what does that actually mean? If those observables, are they ontic or not? Are they something that is epistemic or what? What is, you see, all the juicy questions of quantum mechanics remain open. What do we mean by measurements? Is there a classical mechanics limit? And so on and so forth, right? Most important, and this is what we're going to be talking in the next few lectures, how about the parameter tau or the parameter lambda? How does time enter into this whole picture? You see, here we don't have anything to do with time. Probabilistic theories are developed in order to do inference on the basis of incomplete information, but the inference can be made about the present or about the future or about the past. Where does time enter in this whole development? Those are the subjects for the next few lectures. See you.